Okay, welcome back to GO2. This is the lecture that covers PowerPoint number 4, and we began this lecture on Monday, the 31st of January. That was this past Monday. I'm going to try my best to record the lectures in a format that looks like this for those of you that can't make it to class or don't feel comfortable coming. I'll do my best to get those uploaded in a timely manner, but I am making these as we go, so please bear with me. I'll do my best to get these to you guys. So this PowerPoint is beginning the discussion of atmospheric circulation, as the title slide here says. And so, as you can imagine, that's all about how air is moved around our planet and why. And so that's what these questions here are asking. How does air move? Effects of differing pressure and temperature, and what relationship does this have with the energy balance that we spent a lot of time in the previous lectures covering? And so it does indeed all begin with the energy balance. And so you guys have seen these couple figures before, and what they're depicting here on the top left is the latitudinal distribution of energy that we receive from the sun. That's that solid line there. That's the incoming solar radiation, and the amount of infrared radiation that the Earth is emitting. That's that dotted line there. Okay, and so that brought up this concept, this kind of conundrum, that we appear to have a radiation surplus or an energy surplus in equatorial latitudes, in the subtropics, and we appear to have a net radiation deficit or energy deficit at higher latitudes. Okay, and so we kind of broke that down into the two components here. We said, well, the solar radiation coming in is really a function of the curvature of the Earth. And because the solar radiation is all coming in effectively a parallel path, a straight line kind of from the sun to the Earth, when you take a unit area of that solar radiation and you distribute it across Earth's surface, the amount of area that it covers is dependent upon the angle at which it intersects. That is all to say that at higher latitudes, the radiation intersects the Earth's surface at a steeper angle, and so it's distributed over a larger area. Okay, and we talked about flux, and we said that flux is an amount of something that's distributed or passes through an area. And so if the flux, if the amount of solar radiation is the same passing through each of these circles out here, when it intersects the Earth, it is distributed over a larger and larger area as we move from the equator to the pole. And so the flux goes down. And that's exactly what you're seeing here. The solid line is the solar radiation flux. And it's lowest at the poles and it's highest in the subtropics. Okay. This infrared radiation outgoing is just a product of the surface temperature of the Earth, right? We learned that all objects in the universe emit radiation, and it is inversely proportional to their temperature. And so the Earth is emitting, the whole Earth, everywhere on the Earth, is emitting infrared radiation. It's emitting infrared because of the temperature and that equation that we saw last time. Okay, so we've more or less established that. This is a schematic representation of that. At the equator, there's more energy coming in than there is going out. And at the poles, there's more energy going out than there is coming in. And what that suggests, because we know that the tropics are not just progressively getting hotter and hotter and hotter every year, and the poles getting colder and colder and colder every year, what that implies is that there's some transfer of energy from lower latitudes to higher latitudes. And indeed, that is the case. And that is accomplished, as I've mentioned several times now, through the circulation of the atmosphere and the ocean. So this energy imbalance drives atmospheric and oceanic circulation. Okay. So the Earth is spinning on an axis, and that axis has a tilt. The tilt is currently about 23.5 degrees. And that has direct implications for the distribution of that solar radiation. It means that when we're over here on this side of the sun, it's what we call summer in the northern hemisphere. And that is to say that the northern hemisphere is actually tilted, the axis rather, the North Pole really is tilted toward the sun. June 21st is the summer solstice, or the summer solstice in the northern hemisphere at least. And what that represents is the day at which this perpendicular path of solar radiation is the furthest north that it ever gets. Okay, and that's another way of saying that is that the axis is tilted directly towards the sun on the north side. Okay, and that means that the location of the highest solar flux is up here. It's about 23.5 degrees north of the equator, 23.5 degrees north latitude, which is defined as the Tropic of Cancer. And that's why the Tropic of Cancer is defined at that latitude. It's because that is the northernmost extent that the sun ever gets directly overhead, kind of in quotes there. That is to say, just a perpendicular path directly to the surface. Okay, and conversely, on December 21st, the winter solstice in the northern hemisphere, that same situation is true of 23.5 degrees south, the Tropic of Capricorn. Okay, and so this area in between the Tropic of Cancer and the Tropic of Capricorn, known as the tropics, is defined as the area over which throughout the year the sun passes directly overhead. If you're ever anywhere north of 23.5 north or south of the Tropic of Capricorn, the sun will never reach immediately overhead. It'll always be offset either to the north or to the south, depending upon which part of the globe you're on. Okay, and so that location of highest incoming solar radiation migrates north and south throughout the course of each year. And so we have a special term for that location. It's really referred to as the Intertropical Convergence Zone, or the ITCZ. And it's important to recognize that is not fixed at the geographic equator. It passes the geographic equator twice each year, but it's not fixed there. That zone is responding to the flux of incoming solar radiation. Okay, and so that is more or less captured in this text here. The Tropic of Cancer, also referred to as the Northern Tropic, is the most northerly circle of latitude on the Earth at which the sun can be directly overhead. This occurs on the June solstice, when the northern hemisphere is tilted toward the sun to its maximum extent, currently 23.5 degrees. Okay, the same is true of the southern hemisphere, when the south pole is tilted toward the sun, as is the case when we're over here. Okay. So if you send if you send some satellites up into orbit and you make some measurements, you measure the amount of solar energy coming in as a function. You would do that on the ground, and then you subtract away the infrared emitted. That gives us a net radiation balance for the year, or just net radiation. And so if you average that over the entirety of a year, you get something like this, where zero, that is to say the same amount of energy is coming in as going out. Zero is these yellow-orange colors. Surplus is in pinks and deficit is in blues. Averaged over the year, what you can see is that the maximum surplus is centered right on the geographic equator, and the poles are at a significant deficit. If you look at the months just December, January, and February, however, when it is summer in the southern hemisphere and winter in the northern hemisphere, you can see that maximum radiation surplus or maximum energy surplus is actually down here south of the equator. Similarly, in June, July, and August, it's north of the equator. Okay, that stands to reason. That should be fairly intuitive given our understanding of this, right? This fact, and the fact that our axis has a tilt. And when we're on one side of the sun, the northern hemisphere is tilted toward it. And then 6 months later, when we're on the other side of the sun, it's tilted the other direction, right? The tilt doesn't change. It just sort of goes around the sun like this. If this is the axis, we revolve around the sun like this, right? The tilt doesn't change. The Earth is spinning. You can't really see that, but the tilt doesn't really change. Later in the course, we'll find out that the orbital parameters of the Earth do indeed change on longer timescales, but on a yearly timescale, that's really what we're seeing. Okay, so that more or less establishes this fact, this permanent condition of the Earth, right? And so if we start taking that and applying it to atmospheric circulation, which is our goal here, we need to understand a few basic things about air, just material properties of air, okay? And there are really two that we need to understand. The first one is that air, most substances in the universe, most matter, its density changes in response to its temperature. That's true of all materials, I would venture to say. But what is true of most materials is that as you increase the temperature, if you warm them up, their density goes down. They become less dense. Okay, and similarly, if you cool them down, they become more dense. All right, air definitely follows that trajectory, and so warm air, such as in a hot air balloon, is less dense than the surrounding air because you're taking a torch and you're heating it up. All right, and that causes the balloon to become positively buoyant, as we would say. It's like taking a balloon full of air and pushing it underwater. The contents within the balloon are far less dense than the contents outside the balloon. And so the balloon has the tendency to rise up until it reaches something that we would call neutral buoyancy, right? It'll continue to rise until the density of the air outside matches the density inside the balloon. Okay. If the air out inside the balloon cools for some reason, it will become more dense. Okay, and the balloon will sink, right? So warm air rises and cool air sinks because of its density. Okay, and so if we start here, let's see, is that on the screen? We'll draw one little graph here. Okay, we'll put temperature on the horizontal axis in degrees, and we'll say this is density. We'll just call it D here. Okay, up here we're at high numbers, right? Here's low numbers on this side, the bottom. Okay, and so as temperature increases, we're saying density decreases. Okay, so that's going this direction. All right, well, you can't quite see the D on there, but this is indeed density. We'll put another line right there. I'm drawing in Microsoft Paint here. I will try my best to get an iPad to draw on to make this a little bit easier for me anyway. So air has this property, which most material in the universe shares, that when you increase the temperature, when you make it hotter, its density decreases. Okay, and so warmer air is less dense than colder air, and it will rise. All right, that's really important. That is the first of two critical concepts here, and it has direct implications. If we're heating air in one location, maybe the ITCZ, okay, it becomes warmer, and it becomes less dense as a result. If we have a region that is adjacent to that, where the air is colder, that colder air will have a higher density. And if you put something with a high density next to something with a lower density, the low density material will tend to rise, and the high density material will fill in beneath it. Okay, and that's exactly what happens at the intertropical convergence zone. Okay, there is what we would call a pressure gradient force that carries air from higher, cold, dense air from higher latitudes along the Earth's surface to the intertropical convergence zone. And it does that from both directions, and that's why it's called a convergence zone. Convergence is two things coming together. So in this case, they're the surface currents of air, and they're coming from roughly 30 and 60 degrees, or 30 degrees north and 30 degrees south latitude, and we'll see sort of why that is in a second. But in general, at this point, we're saying that there's this pressure gradient force pushing cold, dense air over to the low pressure zone where there's warm, lower density air. And that warm, low density air is rising in altitude up into the upper atmosphere. Okay? All right. So as that air rises away from the Earth's surface, we know that the source of the warmth for that is coming from infrared emission from the Earth, right? And so the further away from the Earth you get, the colder it gets. We know that. There's snow in the mountains right now. Mount Baldy has snow on the top. Down here in the valleys, it's a cold morning, but it's not cold enough to have snow. The atmosphere becomes colder as you increase in altitude. That's also obvious if you travel in an airplane. They fly at something like 30,000 feet. And if you look at the exterior temperature, which is displayed on a lot of those little in-flight entertainment screens, it's really, really cold, like maybe -30 or -40 degrees. It's freezing up there. Well, way below freezing, actually, right? So the upper atmosphere is cold. The ground is warm, okay? And so if we take warm air, or air, and we warm it, we lower its density, it begins to rise. But as it rises, it cools, okay? That's really important. As it rises away from the surface of the Earth, it cools until it reaches neutral buoyancy. And when it reaches that neutral buoyancy, where the density of that air is equal to the density of everything around it, it begins to move laterally, okay, move sideways. And it does so in both directions, away from the intertropical convergence zone. But as it moves to the side, it continues to cool. And as it cools, the density increases. And so eventually it becomes dense enough that it begins to sink back towards the Earth's surface. As it sinks, it begins to warm up again. And then it's transported laterally into the low pressure zone, where it rises, and it completes this cycle. And that cycle is called convection, and it's present in most systems. Any system, natural system that's being heated from the bottom will most likely display some degree of convection. Okay, and convection is just this cyclical, circular movement of material in response to heating and then cooling, right? Rising and sinking. That's convection. Okay, and so if the Earth wasn't spinning, which it is, everything that we've discussed so far would sort of create this picture, where we have one large convection cell in the northern hemisphere and one large convection cell in the southern hemisphere. You can still see here we have this intertropical convergence zone, where the surface currents of air, the wind, if you will, is coming in from both directions, north and south, and converging on the equator, where it rises because it's being heated, and then moves off in both directions. Okay. However, this is not the full story, because we do live on a sphere which is spinning quite rapidly. And so these single convection cells break down into 3 individual convection cells, 3 in the north and 3 in the south. Okay. And so that's sort of depicted here. What you're looking at here is a cross section of the Earth's surface. Okay. And so we have the equator here at the center, 30 degrees north and south, and up to, looks like 45. And what you see here is that these are the convection cells, okay? So we're looking at a cross section of the atmosphere, and the surface currents, if this is the surface of the Earth, the surface currents are coming in from both sides, coming from about 30 degrees north and south in to the equator, or the intertropical convergence zone more specifically, where they rise, the air rises up, and it then moves in both directions. Gets to about 30 degrees north and south, and it begins to sink back down to the Earth's surface. Okay. And so these convection cells, 3 of them in the north and 3 of them in the south, are permanent features of the Earth's climate, or the Earth's surface system. Okay, and we have a special name for these 2 that are closest to the equator. We call them Hadley cells, okay, named after somebody named Hadley. But this is the foundation of atmospheric science, really, or one of them. And so what it says here, it sort of captures what I've been saying, but we're adding one more, the second layer of complexity onto this, or the second material property of air that's really critical to understanding climate. This says, as warm, moist air rises above the equator, it cools, and the water vapor condenses to form a distinct band of clouds that delineates the intertropical convergence zone. Okay. The subsiding air at 30 degrees north and 30 degrees south warms as it sinks, preventing condensation from occurring. Warm and dry band of air. This warm and dry band of air coincides with some of the largest deserts on the planet. Okay, so that's the second material property of Earth, of air rather, that we need to be comfortable with. All right, and that is that as temperature increases, okay, the ability to hold moisture. All right, I'm just going to type that out because I don't want to write it. ability to hold moisture. All right. You probably can't read that. Let's see, I don't know how we make this larger. All right, like that apparently. Ability to hold moisture. Not a pro at Microsoft Paint here. All right, ability to hold moisture. As temperature increases, well, the ability to hold moisture increases, okay? And that is another fact that most of you probably intuitively understand. When you heat water up, if you get to 100 degrees, all of it evaporates. It is all in the air then, right? If you cool water down, none of it evaporates, okay? You can see this in a lot of ways. It's wintertime right now, and most of our skin is probably dry, especially if you spend a lot of time indoors, because we're taking cool, dry air from outside and warming it up. And when you warm up air, it can hold more moisture. And so there's this idea of relative humidity. When you listen to the weather report, you'll hear about relative humidity. And the reason that humidity is relative, or what it is relative to, is the temperature, right? 100% saturation with water vapor is very different if the air is 0 degrees C versus 100 degrees C, right? That should be obvious. And so as air heats up, we have temperature increasing on the left and density decreasing. On the right, we have temperature increasing and the ability to hold moisture also increasing along with it. Okay, so now if we return to this over here, you have air moving toward the equator, or toward the ITCZ, from both sides. It's getting warmer and warmer as it's doing that, and it's traversing the surface of the Earth. Okay, there's a lot of water down here. And so as it warms up, it drives evaporation and it picks up a lot of moisture. And so when it gets down here into the tropics, it's quite moist. It has a lot of moisture in it, and it's warm. It continues to warm and it rises because the density is decreasing in response to the increase in temperature. But as it rises, it cools because the upper atmosphere is cold, generally. And so it gets to a point where it can't hold all that moisture anymore. And clouds begin to condense, right? The moisture condenses and it begins to form clouds, and then it begins to rain, okay? And that is why it rains a lot in the tropics. That is the sole reason right there. It rains a lot in the tropics because you have convergence and an uplift of air. And as that air is uplifted, it cools and the moisture condenses out, all right? Now, as that air begins to move laterally, it continues to cool, all right? It continues to lose moisture until you get up here into this region, around 30 degrees north or south, and the air is very cold and very dry by this point. It begins to subside or sink back down towards Earth's surface in response to the high density, right? Because the temperature is really low. You can't really see my mouse on that, but the temperature is really low. And so the density is high and it begins to sink. As it sinks though, it warms up, okay? And so it's cold, dry air up here, and it sinks, warming as it does. So when it reaches the Earth's surface down here, it's now warm, dry air, all right? It doesn't want to rain. It wants to absorb water. It wants to evaporate things, right? It wants water to evaporate and to pick up that water because it's warm now and it has the ability to hold a lot of moisture, all right? And so at 30 degrees north and south, you don't find much rain, all right? As that air gets to the surface, it begins to move laterally in both directions. If we focus on this bit, it's coming back towards the Intertropical Convergence zone under the influence of a pressure gradient, right? Because it's cold, dense air here, or colder, denser air here, and it's warmer, lower density air here. So the air moves from 30 degrees north, and 30 degrees south toward the equator, toward the Intertropical Convergence zone, okay, where that cycle repeats itself. And so if you put a little, a note here at each corner of this square, we'd say, well, here we have warm, moist air. Here we have cold, moist air. Here we have colder, even colder, dry air. And down here we have warm-ish, dry air. Okay, and as it moves across, it gets warmer and it picks up moisture until it gets back to the ITCZ and it's warm and moist. It rises, it cools, it drops a lot of its moisture, it continues to cool as it moves laterally. It's very cold, very dry by the time it gets here, subsides, warming up, still dry, but warm now, drives evaporation, returns to the ITCZ, it's pretty moist by the time it gets there, and the cycle repeats. That's convection, and that is the Hadley cell convection specifically, okay? And that's a hugely important concept, core concept of atmospheric circulation and therefore Earth's climate, right? You can see it if you look at the Earth from outer space. There's a distinct band of clouds that is almost always present over the Intertropical Convergence zone. It's right there going through kind of Ecuador. It's right around the equator there. And probably more importantly for sure than the clouds at the equator, if you look at a cloudless image of the Earth, this is just a satellite image that NASA put together, that they removed all the clouds. It's a pretty beautiful image if you look at it in high resolution. What you see is that around the equator there are rainforests, right? The equator goes right through here. There are rainforests. At 30 degrees north and 30 degrees south, there are lots of deserts. There isn't a lot of land down here, but southern Africa, Namibia, South Africa, it's pretty desertous, pretty arid climate. The word arid, A-R-I-D, arid refers to low rainfall, aridity. Australia is obviously very dry. The outback, Central Australia is very, very dry. And there are lots of deserts here in the southern portion of South America as well. It's a little more complicated because of this band of mountains here, the Andes. But in general, at about 30 degrees north and south, we live around 30 degrees north, right? Not too far off, and we live in a desert. I do, right? It's not coincidence. Okay. Atmospheric circulation. This here says also orographic effects. Regional rather than global. This orographic, that word refers specifically to this schematic representation of it anyway. You have the ocean over here in blue, and you have a mountain here, all right? And what happens when you have mountains, large changes in topography, or the altitude of the Earth, their surface, what happens is air is forced up the side of the mountain. And when that happens, the air down here is moved up and it gets colder. And when it gets colder, just like at the ITCZ, it begins to drop moisture. And so on one side, the windward side of mountains generally, or the seaward side, you get a lot of rain. Okay, but when the air gets up to the top of the mountain, it's the coldest it's going to get. Okay, so its ability to hold moisture is at its lowest. Then it goes over the top and it starts to sink back down into the valley on the other side. And when it does that, it warms. And so just like at 30 degrees north and south, when the air sinks back down to Earth's surface, it warms and its ability to hold moisture increases. And so there's not rain on what would be called the leeward side, the back side of mountains. It's what we refer to as a rain shadow. And this effect has a name. It is the orographic effect. And so the orographic effect refers specifically to this. And if we go back to this, you can see this in a ton of different places on the Earth. Washington is a great example. Western Washington is a temperate rainforest, effectively. Eastern Washington is a desert. The Cascade Range is in between. And so as air is forced up in altitude, when it encounters the Cascades, it drops its moisture. By the time it gets to the east side of the Cascades, it's cold, dry air. And so when it comes back down in altitude, it warms and it picks up moisture. It doesn't drive rain. Rain is very rare there. It's the orographic effect. Okay, so if we look back at this schematic representation, this cross section of the Earth here, the Earth's surface going through here, we have the Hadley cells. They're convecting. Okay, this up here, we're looking at the upper atmosphere, about 12 kilometers. It says here. Down here, we're looking at the surface of the Earth, okay, in cross section. So these two arrows that are highlighted in red here are surface currents. I've been using that term repeatedly. Surface currents, that is to say they're effectively the wind that we experience on the surface, right? Currents in air are wind, effectively. And so if you look at the globe, the global distribution of air, of wind patterns at the surface, it is directly responding to this, all right? And it does so in kind of a complex way, and I'll try to walk us through it, and we'll try to get to the end of it here. But in general, these Hadley cells are forcing air from 30 degrees north and south toward the equator, okay? Similarly, from 30 degrees towards 60 degrees, there's another convection cell operating, and the surface current there goes towards 60 degrees. Similarly, there's a third, as I mentioned earlier, convection cell at the pole, both the north and south pole, and they convect in the opposite direction, okay? And so if you look at the Earth's surface, it's kind of just like from the side, the whole Earth, here's the equator, 0 degrees, 30 north, 60 north, and the North Pole. These arrows represent what would be the surface currents, right? The winds, the surface winds. If what I've said so far was the whole story, which it unfortunately isn't, we have to add one more layer of complexity to this until we arrive at this, which is really the sort of most generalized sort of introductory level depiction of the atmospheric circulation that you could make. In here you see these sort of donut-shaped convection cells. These are the Hadley cells here and here. And air is being brought from 30 degrees toward the equator from both directions. It converges, it rises, clouds form, right? This band of clouds. It cools and it returns to the Earth's surface around 30 north and 30 south. Okay. Now, what you'll see here is that these arrows here are not straight. They curve. Okay. They curve here. If you look at just these arrows, these are going from 30 toward the equator. These ones are going from 30 to 60, 30 to 60. And then here at the pole, you have return flow at the surface from the pole towards 60 degrees. Each one convects independently. This previous figure, again, shows those surface currents, right? These two lines here are the same as these two lines here, okay? And they're representing the same thing as these curved lines here. Right? These are going from 30 toward the equator in both directions, but they curve. Now, they curve because of the Coriolis effect. And so the Coriolis effect is one of the more sort of tricky concepts in this class that we encounter. And it happens, it exists. And so I generally tell people that you can just sort of take our word for it and just understand that objects in the northern hemisphere bend to the right, appear to bend to the right off of their trajectory, or you can try to understand it on another level. There are a lot of really good videos on YouTube that'll show you videos of people often on a merry-go-round at a playground, and they're throwing a ball back and forth, looking at how it appears that ball changes directions or travels. But I would encourage you to check those out. There's some great videos about it, but in a purely conceptual description, this is what's happening. The Earth is spinning on its axis. And that means that each day, if you're standing anywhere on the planet, you're going to experience one full rotation around the axis. Now, if you're standing at the equator, that means you're going to travel something like 24,000 miles around in a big circle. But if you're standing at the pole, you're not traveling anywhere at all. You're just spinning in place. And so your velocity here, toward the east, is significantly higher than it is up here. And that's true of anywhere on this. If you're at point B here in, say, 1 hour, you travel this far, whereas if you're down at the equator, you travel this far, which is further. Okay, and that is to say that your velocity is higher to the east down here than it is up here. Okay, and so this conceptual sort of description of it would have someone at point A firing a cannon or something, some type of projectile that they shoot directly north toward the person at B. Okay, now it takes some amount of time for this object to get to point B. In that amount of time, the person at point B would have traveled this far, and the person at point A would have traveled this far, okay, a little further than the person at point B. And so this object that they're firing or sending due north is actually not only traveling north, because when it left point A, it had some amount of velocity towards the east. And so rather than going due north, it's actually going to go in a straight line over to here. But if you're standing at point B observing this, okay, that's where this all comes together. If you're standing at point B observing this ball or object traveling toward you, at the moment that the person at point A sends it to you, it'll appear as though it's coming directly at you. But as time progresses, it'll appear to you as though the path of the ball begins to curve. And it'll curve off and miss you. Now, I've been saying that objects in the north are bent to the right, and objects in the south are bent to the left. That is referring to their path. If you're walking along this arrow, the path is bending to the right. If you're walking along this arrow, the path is bending to the left. Okay? That is true of all objects in the northern or southern hemisphere. If you're right on the equator, that's not true, right? If things are moving strictly along latitude, that's not true. But anything that's moving in a northern or southern direction, it is true. It is true because as you move away from the equator, the ground underneath you is moving more slowly than it was where you came from. Okay, and that has a profound effect. It creates the Coriolis effect. This figure here is a kind of a graph of, or an infographic really, of tangential velocity. So just the easterly, sort of the instantaneous eastward velocity that an object has when it's on the Earth's surface. And you can see that at the poles it's 0 because it's just spinning in place. But at the equator it's traveling something like 1,000 miles an hour. All right, because the Earth spins in 24 hours once, and the Earth is about 24,000 miles in circumference at the equator. So it's going about 1,000 miles an hour. Okay, and so that has profound implications for circulation in the atmosphere. Okay, so if we go back to sort of this figure, right, and we apply the Coriolis effect, then we have something that looks like this, right? These arrows coming, the Hadley cells, right? These Hadley cells, the surface currents are coming from 30 degrees toward the equator, both directions. But in the northern hemisphere, they're bent to the left. And in the southern hemisphere, bent to the right, right? If you're walking along this arrow, you're bending to the right. And if you're walking along this arrow, you're bending to the left. Both of them converge at the ITCZ, and they're moving toward the west, right? To the west. They're moving from the southeast to the northwest here, and from the northeast to the southwest there. And that creates this band of wind here, just north and just south of the Intertropical Convergence zone, that is known as the trade winds. Okay, winds are named from the direction from which they blow, and so the northeast trade winds are the winds that are coming from the northeast and coming to the west, to the southwest. Similarly, the southeast trade winds are those below the equator, the southern hemisphere, that are coming from the southeast and moving to the northwest. Now, this was really important. sailors realized this a long time ago. So they're known as the trade winds, because if you're trying to do intercontinental trade using sailing, right, ships with sails for power, then it'd be nice to know where you can get into a current, an air current, that is, that will blow you to the west, right, to get across the ocean. Similarly, if you look at the circulation cell up here between 30 and 60 degrees, what you find is that there are winds that are consistently blowing from 30 degrees towards 60 degrees, but that in the northern hemisphere they bend to the right, and they kind of coalesce into a band that is known as the westerlies. Okay, it's in North America we call it the jet stream. It flows more or less at the Canadian-U.S. boundary border. The westerlies. We also have westerlies in the southern hemisphere down here, or between about 45 and 60 degrees north. There is a continuous flow, a continuous atmospheric current at the Earth's surface that flows from west to east. Okay, and so those are permanent features of the Earth's atmosphere. It circulates in convection cells, 3 of them to be exact in the north and 3 of them in the south. The middle ones we call Hadley cells. And as air convects through that cell, it creates these surface currents as a response to pressure gradients, right? Air moves at the surface, and as it does so, it is subject to the Coriolis effect, which causes it to bend on its path. And in the northern hemisphere, objects are bent to the right. In the southern hemisphere, they're bent to the left, causing these permanent features known as the trade winds. Okay, the northeast trade winds and the southeast trade winds, and the westerlies. Okay, up here. Westerlies down here. Those are permanent features. As we'll find out in the next lecture, atmospheric circulation in part, along with the Coriolis effect, really drives oceanic circulation as well. It's a little bit more complicated because water obviously can't flow over top of continents, right? It's stuck in its ocean basin, but it responds to a lot of the same things. Temperature, pressure gradients, those cause ocean water to move, just like they cause atmospheric fluid, which is air, to move. And so that's the end of this section, this sequence of slides called Lecture 4. Really important take-home messages from this. Obviously, these two little, very kindergarten-looking graphs that I drew over here, as temperature increases, the density of air decreases. Its ability to hold moisture also increases, okay? So as you warm air, it can hold more moisture and its density generally decreases, all right? And so those two things, coupled with the fact that the sun's radiation doesn't get distributed evenly over Earth's surface, those kind of 3 points there explain all essentially of the most the largest scale phenomenon that we observe in the Earth's climate, all right, or the Earth's atmosphere. And this is, obviously plays a major role in climate, right? If we go back here, if climates are really, climate zones are these regional descriptions, well, the Sahara Desert is a big region, right? It has a distinct climate from sub-Saharan Africa or, the Mediterranean. It's very different. And it is so because of large-scale atmospheric circulation. And so that's where I'll end it here. And the next set of slides will pick up with oceanic circulation. So thanks very much.